Hello there, this is Jude Socrates. Welcome to today's video on infinite series. Now in our last video, we introduced the concept of a power series of representation, the domain or the interval of this representation, and its radius of convergence. Today we're going to learn how to manipulate these representations. In other words, we're going to perform some algebra on them. There are three things which we'll talk about: how to perform a substitution on a representation, how to add two representations, and how to multiply by a scalar. That's probably the simplest part of this video. So what I'm going to do is we are going to walk through section 3b of my textbook, and then at the end we are going to discuss a new example. All right, let's get to our textbook. Okay, here we go. So we actually have exactly one example of a representation, meaning a power series and a function which is represented by this power series. We have exactly one equation that looks like this. Power series on the left equal to a function on the right, and the known domain. X must be between -1 and +1. So the first manipulation that we're going to talk about is basically just a substitution. And of course, you probably have or remember or associate substitutions with u substitutions, where if you have an integral, you might have to make 2x equal to u, for example, solve for dx, plug it in, blah, 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 before you can apply an integral formula. So it's almost the same thing with the representation. The first thing we're going to do is change the variable x into u in this representation. With practice, you'll be able to skip that step, but let's think of it as training wheels. So we see x, x, and x. 3 times that x appears in this equation, along with the domain, of course. This is all one package deal. So change the x to u, change the x to u, change the x to u. Summation n from 0 to infinity, u to the n, is just 1 over 1 minus u for all u between -1 and 1. So now we are going to perform two substitutions, two examples of substitutions. We will let u be 3x, and so we get 3x to the n equals 1 over 1 minus 3x, for all 3x between -1 and +1. Next, we will make u be x squared, and so we will get x squared to the n equals 1 over 1 minus x squared for all x squared between -1 and 1. Okay, so that's the basic idea, but we're not going to stop there because we're going to simplify this and this using the rules of exponents. Okay, so you probably know where we're going here. A times b to the power n is the same as a to the n times b to the n. Everyone should know that. And x to the a to the b is x to the a times b. You multiply the exponents. Okay, there's something else we're going to do. This does not look natural, so we're going to isolate x. And same thing here, x squared between -1 and 1. We're going to isolate x. All right, so let's scroll down. So there is what I was saying, and let's stop over here. So we have 3x to the power n, that's 3 to the n times x to the n. X to the 2 to the n is x to the 2 times n. So this first domain is easier to simplify. This means that 3x has to be between -1 and +1. Divide all parts by 3, x must be between -1/3 and 1/3. Or in other words, x must be between -1/3 and 1/3, excluding both endpoints. So this is the effective domain or interval of convergence for that first example. So what happened? It went from -1, 1 to -1/3, 1/3, okay? So we can think of that as a contraction. If you multiply x by 3, you're going to have to pay for it by shrinking your domain by a factor of 3. dividing your domain into 3 effectively. Okay, so what about the next one? You want x squared to be between minus 1 and 1. What does that mean? X squared must be between minus 1 and 1. But isn't x squared already positive? Or it could be 0, right? So one way to think about it is to look at the graph of the x squared function, the basic parabola. Okay? We want to know when is x squared between minus 1 and 1, right? So I'm generalizing here. I want x squared to be less than c, where c is a positive number. What we want is x squared less than 1. Okay? So if this were y equals 1, well, when is x squared equal to 1? X is either positive 1 or negative 1. Right? So basically, we get the same interval. If you want x squared to be between minus 1 and 1, then it's the same as x must be between minus 1 and 1. All right, so we get these two completely simplified and full-fledged representations. Summation n from 0 to infinity of 3 to the n times x to the n is 1 over 1 minus 3x, and x must be between minus 1/3 and 1/3, excluding the endpoints. Summation of x to the 2n must be 1 over 1 minus x squared, and x simply has to be between minus 1 and plus 1, as before. So as a bonus, we have a graph of the two functions. Here's 1 over 1 minus 3x, and here's the partial sum up to x squared. And of course, we can see that you can barely tell them apart within a small interval. This is supposed to be valid between minus 1/3 and plus 1/3. Okay, so of course there is some separation as we get closer to 1/3. The second one is valid between minus 1 and plus 1. So of course we have vertical asymptotes at plus or minus 1 for 1 over 1 minus x squared. Before it was just x equal to 1, but now minus 1 is also going to make the denominator 0. The partial sum of the first three non-zero terms will go up to x to the power 4. And again, we can tell here that the two graphs are almost identical, let's say between negative 0.5 and positive 0.5. So the other two algebraic manipulations that we will perform involve adding two representations and multiplying one representation by a real number. So suppose you have two representations and they must have the same center, x equals a, because otherwise it'll be almost impossible to add these two infinite series together. So if they do have the same center, then you can simply add on the left side f of x and g of x. On the right side, when you add these two series together, they have a common factor of x minus a to the power n. So their coefficient is simply going to be cn plus dn. So you have summation n equals k to infinity, the same starting point for both series. And the coefficient is cn plus dn times x minus a to the power n. When is this going to be valid? Well, x must be common to both I1 and I2, the two domains. So we take the intersection of these two domains. Where do they overlap? If they have the same center, then one of them might be bigger than the other. We choose the smaller domain because that's where they overlap. All right, and if you multiply both sides of a representation by k, you can bring the k inside the summation. We've seen that before. So k times f of x is the same as summation n equals k to infinity, k times cn times x minus a to the power n. And we keep the same domain, I1, which is the domain of our original representation for f of x. So more generally, if you multiply both sides of this representation by a power of x minus a, and we'll make it a positive integer, okay? So it's kind of like if you have x squared times x to the n, you'll just get x to the n plus 2. We know how to add or multiply two power expressions. We simply add the exponents. So if you multiply both sides by x minus a to the t, then this becomes from x minus a to the n, we're going to add t, x minus a to the power n plus t. And we have the same coefficients, c sub n, and the same domain, I1. All right, so with that, let's go to our workroom. We haven't been there yet. We're going to work on one function. It's going to be a good one, and it will involve substitutions, multiplying representations by a real number, and adding two representations together. All right, so here's the function that we're going to be working on for the rest of the video. God, where did that come from? 11x plus 103 over 5 minus 2x times 7 plus 3x. Okay, so we have two vertical asymptotes going on here. One at 5 over 2, one at negative 7 over 3. It's kind of like the second representation, you know, where we had 1 over 1 minus x squared. Vertical asymptote at plus 1 and minus 1. Okay, this looks a lot nastier though. So we're going to find a representation for this. It will be centered at 0 because it's going to be based on the geometric series, the only representation we know about. And we will look for its domain. So just like our previous examples, we will look at the first few partial sums in GeoGebra. All right, so guess what? Speaking of partial, we know about partial fractions, right? So partial sums will come later. We want to decompose this function into two partial fractions. We have two factors in the denominator. One of them is 5 minus 2x, power 1. So it's just power 1. And the other is 7 plus 3x, again, power 1. So we simply have two terms. We will need the numerators, right? What are a and b? Okay, so you remember how to do this? Multiply the denominators across. So we will have 11x plus 103 on the left equals a multiplied by 7 plus 3x. So that factor goes with the a. And plus b multiplied by the 5 minus 2x. Okay, so we need a and b. We do have two numbers. We do have two numbers that we can plug in. They're not the greatest because they're fractions, but there's a reason why I wanted to give you a problem with fractions. So let's let x be 5 over 2. And what do we get? So we get 11 times 5 over 2 plus 103. And on the right, b goes away. So we have a surviving times 7 plus 3 times 5 over 2. Okay. So what do we get? So 103 times 206 plus 55 is 261. Is that right? Do I trust myself this early in the morning? Ooh, yes, 261. Oh, look, it also did the right side for us. 14 plus 15 is 29. So yeah, we get this equation. Thank you, Maple. And solving for a, we can cancel the 2's. And a is 261 divided by 29. Keep your fingers and your toes crossed that this is exactly 9. Yeah, all right. So we get a nice integer numerator, even though that numerator looks nasty. Okay, it actually gives us a very nice numerator for a, and of course it will also give us a nice numerator for b. Okay, so next we will let x be negative 7 over 3, and so we will get yeah, you know what, let me copy this. would be easier to do our plugging in. X multiplied by, 11 multiplied by -7/3. And so this time A goes away as it should. And X is -7/3. Okay, so B survives. And, okay, so I'll do it one at a time this time. We want to simplify this. So 103 times 3 is 309 minus 77. Good grief. So that is 232 over 3. And on the right side, what are we going to get? We will get, simplify, we get 29 over 3. Ooh, there's 29 again. What's going on here? 232 over 3 is going to be 29 over 3 times B. And of course, B this time is going to be 232 divided by 29. Fingers crossed, toes crossed, and we get 8. So one of them is 9, one of them is 8. All right, nothing wrong with that. So we get our decomposition. Let's copy that. Our A was the 9, and our B is the 8. Okay, let's check our answer because it came from down here. Are you there? Are you there? Yes, that's where it came from. 9 over 5 minus 2x plus 8 over 7 plus 3x. Now you know how I make my examples. Okay, that is our partial fraction decomposition, and now we need to work on substitutions. All right, so what we're going to do is we will take each term separately, and we will create representations for them by applying the geometric series. All right, but in order to make this work, we need 1 in the numerator, that's a 9, 1 minus u in the denominator, that's a 5, and that's a minus, but that's a plus, okay? So we need that to be a 1, we need the 7 to be a 1, we need the plus to be a minus. Okay, so we have to do some magic. No, it's not magic, it's algebra. So let's start with the first one. What we're going to do is we're going to factor out the 9, easy, and the 5, okay? Maybe a little bit tricky. So we're going to multiply two things together. We're going to take the 9 out, and we're going to take the 5 out. I erased too much. So that 9 is now just 1. 9 times 1 is 9. I need a 1 here so that I get 5 times 1 is 5. But the minus 2x should now become minus 2x over 5. Okay? So now this looks like 1 over 1 minus u. And so u is going to be 2 over 5. Okay, so thus, let u be 2 over 5x rather. 2x over 5 in the geometric series. All right, so we will copy this, and we are going to substitute 2x over 5 for u. Okay, let's put some space here. So let's make a fraction. We can use this one. 2x over 5 to the n. And we can keep it in this form on the right. And remember, you also have to change the domain. So 2x over 5 must be between minus 1 and 1. I think it'll look better with a fraction. There you go. So that is our representation. And, well, let us simplify it. So just like we saw in our textbook, we will expand this by using power rules. So the power n will go over the 2, over the x, and over the 5. All right. And what about the domain? We will multiply the left side by 5 over 2, which means that we will be going from minus 5 over 2 to plus 5 over 2. That might make you a little bit uncomfortable. So let's also do that in detail. Okay. So, yeah, the left side we can work on. So we will get 2 to the n, x to the n, over 5 to the n, n, not 5. Okay, everything is n. Right side, and so let's think about this. We want 2/5 x to be between -1 and +1. Multiply everything by 5. You want to do this one at a time. -5 less than 2x less than +5. Now divide by 2, so -5 over 2 less than x less than 5 over 2. All right, so we can now change this to x is simply between -5 over 2 and +5 over 2. All right, that's our domain from -2.5 to +2.5. Okay, so now we need a representation for the second one. We need 8 over 7 plus 3x. All right, next job. We again need the geometric series. Whoops, let's center it, just like the other one. What about me? Okay, so we are going to break up this fraction into 2 factors. So there will be a times in between. Yeah, actually, you know what? Why don't you pause the video right now and then try to do what we just did in the previous step. Okay. Pause it now. You're back. So we divide out the 7. That's now a 1. That's now a 1. 3x over 7. Whoops, not x. Over 7. So we want a 1 minus u though. So let u be 1 negative 3x over 7 this time. All right, so in our geometric series, we're going to have this. We're going to need negative 3x over 7. Borrow this. Minus 3x over 7. Thank you much. And we will have 1 plus 3x over 7 here. And we want minus 3x over 7 to be between -1 and +1. Okay. Simplify. So this time we have a -1 to the n to deal with. It's going to be an alternating series. So, or at least it will appear to be an alternating series. -1 to the n, 3 to the n, x to the n, over 7 to the n. Okay, what about the domain? Should you be bothered by the negative sign there? Well, if you start out between -1 and 1, and you take care of the minus first, the 1 will flip to the left as -1, the -1 to the right as +1. It's the same thing. So our domain is going to be only x is between -7 over 3 and +7 over 3. Okay. So that is our domain for the second representation. So now we have to put these two representations together. Oh wait, there is the 8 over 7 and the other thing. So we have to do that next. All right, now we get to put it all together. Big picture, what have we done so far for this function? We did a partial fraction decomposition, found the numerators. Each of them we turned into a form that will allow us to apply the geometric series formula. And so for the 1 over 1 minus 2x over 5, we got this representation. For the 1 over 1 plus 3x over 7, we got this representation. So basically, we're simply going to put these things together from this, and from this, and from this, and from this. And we are going to get the domain by finding the intersection of these two intervals. Okay, so who is bigger, 5 over 2 or 7 over 3? They're both bigger than 2, but 5 times 3 is 15, and 7 times 2 is 14. Close, but no cigar. So 5 over 2 is bigger than 7 over 3. 7 over 3 is smaller. We picked the smaller interval because we need the overlap. Okay? If you pick someone from the bigger interval, it might not be inside the smaller one. You might be outside the bounds for the smaller interval. So it has to be the smaller one, 7 over 3. Okay, so shall we? Let's make a copy of this because we're basically going to simply plug in everything we have so far. Okay, so let me put it down over here. And let's build it up. So we said that 9 over 5 minus 2x is this. So let's put that over there. And 8 over 7 plus 3x is this thing. So we add that together. Okay, and then what did we do? We said that this is the same as this representation. So I'm going to copy all of this. And the function 1 over 1 minus 2x over 5 will be replaced by the power series. This guy over here. And similarly, our 1 over 1 plus 3x over 7 is this power series over here. So we can do that replacement. Okay. All right. And while we're here, let's might as well include the domain. So this, yes, wonderful. There is our representation. What we need to do now is combine these two series together. And the first thing we're going to do is we're going to put the constant coefficients inside. Right? So a property works forwards and backwards. If the constant were inside, we can take it outside. If it were outside, we can take it inside. Okay? Back and forth. Okay, so yeah, let's copy this whole thing. So this 9/5 we're going to bring inside like so. And this 8 over 7 we'll bring inside like so. All right. So that's it. And yeah, sure. We could have copied all the way up to the domain. Okay. So now we got to simplify this a little further because there's a 5 here and a 5 to the n, a 7 here and a 7 to the n. So we can put them together into a single power of 5 and 7. So that becomes just 9. And that becomes n plus 1. 5 times 5 to the n is 5 to the n plus 1. This becomes just 8. And this becomes 7 to the power n plus 1. Okay, and to prepare ourselves to combine these two series into one single series, we're not done until it's just one summation. Let's put the x to the n to the right, because this whole thing is one coefficient, c sub n. This whole thing is another coefficient, d sub n. Okay, so copy one more time. And we will have a single summation. So we will have a single coefficient. That's the c sub n, x to the n. And we will add the other coefficient. This is the d sub n. Add those two coefficients together, and that becomes our single representation. All right, and the domain, of course, is going to be from minus 7/3 to positive 7/3. Okay, so if you didn't have an answer key, how will you know that this representation is correct? Well, we can check in GeoGebra that if we take a partial sum, let's say, of 3 non-zero terms, then the graph of the partial sum will be very close to the graph of this function. Okay, so what we have to do is we're going to find the value of these coefficients for small values of n. Okay, so let's see if Maple will agree to compute that for us. Can you find that? Oh yeah, thank you so much. 103/5. So we'll plug in 1 and 2. N equals 1 and n equals 2. How about 3? Okay, 3 is there. So we get, and then we get, oh wow, nasty. And even nastier, yeah, of course, the powers get bigger and bigger. 5 and 7 have nothing in common. Okay, so we have those coefficients, and therefore our partial sum will go up to x cubed. Okay, so let's call it g of x. This is basically our S3. In keeping with our convention for partial sums for power series, that 3 means the highest power of x. Okay, so this is C0 plus C1x, x to the 1, plus C2, x squared, and then C3, x cubed. Okay, so we definitely do not want to type all of that in to GeoGebra. So fortunately, I can simply cut and paste the whole thing into GeoGebra. I will see you there in 1 second. Woohoo! Here we are. Cut and paste, cut and paste. And I'm feeling good because we only have to match the appearance. The graphs should look similar only between, what did we say, minus 7/3 and positive 7/3. Okay, so this is a big picture of both the original function. Let me hide the S3. So this is our f of x. There's a horizontal asymptote, the x-axis, and we have 2 vertical asymptotes, as we said. One at 5/2, one at negative 7/3. Let's look at the partial sum. It's this one. Let's see it by itself. It's a cubic. So yeah, there is no vertical asymptote. It's simply a polynomial. Okay, but they are supposed to look the same if we zoom in between minus 1/3 and plus 1/3. This is the only domain that matters, between minus 1/3 and plus 1/3. We're getting there. We're getting there. Yep, minus 0.5 and plus 0.5. Yeah. So, hang on a second. Here we go. I adjusted the scale. You can appreciate it a little better. We only have to go between plus 7/3 and minus 7/3. Actually, we can zoom out some more. Yeah. We only have to go between minus 7/3 somewhere here and plus 7/3. So, of course, as we go further away from 0, you do see some separation. Okay? But if we zoom in, let's say even between minus 0.5 and plus 0.5, you can see, oh my goodness, yeah, you can barely tell those two curves apart. They're just about hugging each other. Okay, so that is our introduction to the algebra of power series representations. So in our next video, we're going to do calculus on these representations. You have a function. Can you differentiate it? But you also have a power series. Can you also differentiate that? We're going to find out. All right, so until then, I hope you enjoy the rest of your day. Bye.